Hey there! I mentioned in the last video that we're going to take a look at 5 examples in this video that we can do with an embedded derivative that we've done before as either homogeneous or a Bernoulli equation. And we're going to take a look at 5 of those examples, the first 4 of which we've done as homogeneous, and we're going to see that embedded derivatives can sometimes make these a lot more streamlined because we don't have to set up the problem as much. So I'm going to show you that with 5 examples, 4 of which are homogeneous, 1 for Bernoulli, and see that sometimes this can be a lot more streamlined, a lot easier. It's one of the techniques I look for right off the bat when I see a differential equation is, hey, do you have a piece of it that's a derivative of a function of y? And so that's the whole idea. If you don't remember from the last video, what we're looking for here is a manner of substitution that you can call a function of y equal to v, and then the derivative of that function of y with dy dx is on the other side typically, or somewhere else in your differential equation. And then we can make a nice substitution, saves a lot of energy. So I'm going to show you that. Does it work all the time? No, but when it does work, man, sometimes it's nice. And so if you want to go back and compare these 4 examples with the homogeneous that I'm talking about and the last one with Bernoulli, you're going to see that it's a lot easier. So here's what we're doing. We're looking for a function of y, like y squared, that when you take a derivative of it, you get another function or a piece of the differential equation that's up there. And this is our substitution. So when we look at this, we go, is there a piece of this that I can take a derivative of that's also in my differential equation? Well, there is. Now, I want to just say something here. Just like we did with those u subs and integration, we're not super concerned about matching up our constant coefficients. This one happens too, but you don't need that to happen. And so just like a u sub, we're really just looking at, do the variables match up and do we get a dy dx? So if you remember with all of these substitution techniques, every instance of y has to get wrapped up in a v. So in this case, we're going to wrap up a function of y as v. The derivative of that function of y with dy dx has to be somewhere else in your differential equation. Let's take a look at it. So here I'm looking at it going, okay, is there a function of y that I can call v? Yeah, 2y squared. Okay. Is the derivative of that in there somewhere? Well, derivative of 2y squared is 4y. Could I work with that? Yeah. But could I just take y squared equals v instead of that too? You can do that. You don't need to include those constants all of the time. And so if we say, let's just do v equals y squared. Notice how the entire function, all the y's on the right-hand side are going to be wrapped up in a v. You have to have that happen for a substitution. We can't have 3 different variables in a differential equation and work with it with these techniques. So we can't say, okay, well, we're going to just wrap up some of the y's as v's, and then we'll have our x's, and we'll have some v's and y's and x's. That doesn't work so well. So every instance of y has to somehow work in the substitution as being involved in a v sub somehow. So let's call v equals y squared. All right, what now? Well, we're going to have to get rid of that dy dx, and that infers that we're going to have to take a derivative. So we're going to have a dv dx, no problem. Remember that v is a dependent variable, and y is a dependent variable, and x is our independent variable. So we're taking a derivative on both sides with respect to our independent variable. So dv dx, but on the right-hand side, what that means is that we're going to have a chain rule. Yeah, we're going to get 2y, but because y is a function of x, you have a dy dx that you're going to have to put up there. And that's exactly how the embedded derivative works. So we take a look at it and go, oh, hey, look, if I call this y squared v, so I'm going to get 2v, and on the left-hand side I have a 2y and dy dx. The 2 and the y and the dy dx are going to get wrapped up in dv dx. Yes, we're still going to have an x. That's okay. We just need 2 variables, one independent, so we need x's, and one dependent, either y's or v's. But if you're going to change some y's, you got to change all the y's. In this case, that does it for us. So I'm going to rewrite it just a little bit, and then we're going to make our substitution. I'm going to try to go a little quicker on these examples because we have the technique. I'm just showing you that this can work another way besides homogeneous or Bernoulli equation or one of the other techniques that we've done. If you remember, with homogeneous, what we would have had to have done is divide both sides by 2xy. We've got a fraction of x over y, so we had to reciprocate that, change the exponent, v to the -1 power, and then we'd have y over x, that would be v to the first power, and then we had to go through and deal with that. This is much nicer for us, and we're seeing that. So I'm going to write this as x times 2 dy dx, no problem. On the right-hand side, x squared plus 2y squared. And now we can see our substitution. Every instance of y is going to get wrapped up in some form of v. So x squared, leave it. The 2, hey, that's not part of your v. You need the 2. But y squared we replace with v. On the left-hand side, we still have the x, but 2y and dy dx, the 2, the y, and the dy dx, this whole thing here, that's dv dx. And you go, well, but that doesn't look all that great to me. Can we work with it? Well, of course we can work with it. Let's go ahead and see what's really going on here. Do we have x's and v's and no y's? Yeah. Do we have a dv dx and v to the first power? Yeah, where it's added or subtracted. Oh yeah, hey, that looks a whole lot like something that's linear. So let's go ahead, let's write this as linear. So I'm going to subtract our 2v on both sides. To get something in a linear format, we're going to have to get dv dx all by itself. So we're going to have to divide by x. And when we do that, we're going to have a domain issue. We've talked about it now several times. Let's write that as we go. So if x does not equal 0, then we get dv dx minus 2 over x times v equals just x. We divided everything by x. That's looking pretty good. Now we can go ahead and find an integrating factor. Now we can multiply everything by it, and then we'll be fine. So let's find our rho of x e to the negative. Let's just pull that 2 out too. Negative 2 integral 1 over x. Well, let's see. That's negative 2 ln absolute value of x. Could I have made this greater than 0 and not had to deal with the absolute value? I could have, but we're going to get a 1 over x later. And so I'm not going to do that because that absolute value needs to be inside of an ln. And so I'm going to put as few domain restrictions as possible. But we are going to notice that that absolute value is going to disappear because we have it to a power 2. So we have this as if we take that negative and apply that, that's going to be 1 over absolute value of x. But then if we square everything, when you square the absolute value, it's saying you're going to get something positive no matter what because of that x. So that's going to disappear that absolute value anyway. So we're going to get this 1 over x squared. E to the ln, gone. Composition inverse functions, you got it. We're just going to get 1 over x squared. Let's multiply that everywhere. Let's see what happens. So from here, we know that we had a dv dx. We know we have a minus 2 over x times v, and then we have this x. And if we multiply that integrating factor of the rho of x on both sides, it's going to distribute. We're going to get 1 over x squared. Looking good. And 1 over x squared, no problem. And 1 over x squared. And let's simplify what we have. This would be this 1 over x squared dv dx minus 2 over x cubed times v equals 1 over x. And we're going to get another absolute value of x. So could we define this as greater than 0? Yep, you could, but we're trying to put as few domain restrictions as possible and simplify as much as we can. Since we wouldn't be able to simplify with this, you'll see it in a minute, I'm going to leave it just x is not equal to 0. Okay, let's check our work. As the derivative of this equal to this, it is. It's looking awesome. Now we know with linear that the left-hand side is the result of a product rule of 1 over x squared times v. On the right-hand side, we still have 1 over x. Let's do an integral on both sides with respect to our independent variable x. On the left-hand side, we get 1 over x squared. On the right-hand side, we get ln absolute value of x, yes, we need it, plus c. We're almost done. Whenever we do this, we've got to replace v at the very end with whatever function of y we use. So in our embedded derivatives, v is always a function of y that doesn't include x's. So that we can, well, that's not true. I'm sorry. It's usually a function of y that doesn't include x's. We will see in the last example we can alter that. But what we're trying to do here is replace that v with whatever function we used, we got rid of. So in our case, we got rid of a y squared with a v. Let's solve for v first, and then we're going to have to replace that v with that y squared. So multiplying both sides by x squared, we get that x squared and then times ln absolute value of x plus c. I mentioned something just a minute ago. I said that because we're not going to be able to simplify our x squared to the absolute value of x, we really didn't need the domain restriction of x greater than 0. So if you had to get rid of that absolute value, you would have done that. We don't really have to do that, so we're going to leave it. And then our last step, because we used our substitution to get away from y squared into v, now we're going to use it to get away from v back into y squared. That is about as good as we can make it. So again, is it necessary all the time to use one particular technique for every single problem that you get? And the answer is no, it's not. Sometimes we can have sometimes a different technique will give us an easier way to get exactly the same answer. Same answer, but we avoided all the homogeneous setup. So we didn't need to divide by 2xy. We didn't need to define some of those things the same way, and we still get the same thing. So just a quick look at that. Make sure that when we're doing this, the key points here are that you have to wrap up every instance of y in some form of v. Either v itself, y squared becomes v, or dv dx. So the derivative of your function of y equals whatever derivative you have on the left-hand side connected to a dy dx. Then we substitute y squared equals v, great. The derivative equals dv dx, and typically works out very, very nicely. Let's take a look at another example, and then we'll come back with two more and our last one, which is really interesting. You gotta hang out for the last one. So next up, okay, we see this, so could we do it homogeneous? Yes, yeah, we could divide everything by xy squared. It's actually not all that bad. What's going to happen is looks like we have v to the negative 2 maybe, I'm not sure. But we divide everything by this, and then we'd have to go through, do homogeneous, create a separable equation. Not really a huge issue, but can we do it differently with an embedded derivative? Well, let's take a look. Do you see a function that if you take a derivative of it, you are going to get something on the left-hand side? Typically, it's on the left-hand side. So, in other words, do you see a function of y that when we take a derivative of it, the derivative is there with a dy dx next to it? Yeah, I see that. If I call v y cubed, and I take the derivative of it, both sides dv dx, three y squared dy dx, implicit derivative, we got chain rule. We go, wait a minute. No, that's not the same. This one, that says 3, that says no 3. What are you doing? Look, just like we did with a u sub on integrals, man, just solve for the piece you want to replace. So if dv dx equals 3y squared dy dx, but you don't want the 3, let's just divide both sides by 3. Then we have 1/3 dv dx equals y squared dy dx. That way we can replace all of the y squared dy dx. We'll leave the x. We'll replace all of the y squared dy dx with this 1/3 dv dx. Does that make sense? I hope that makes sense in your head, that you're going, oh yeah, okay, it's just like a u sub. It's basically the same thing. We're just doing sort of a double substitution. We're calling the function of y equal to a v. Then the derivative of that is going to yield a dv dx. Replace the function of y, the derivative of the function with y with dy dx, with whatever that equals. So let's solve for what we want to replace, and that's the idea. We're replacing this with v. The derivative is 3y squared dy dx. We only really want to replace y squared dy dx. So solve for that piece in your derivative. and then we can replace this whole thing with 1/3 dv dx. Let's do that now. So maybe you should try it on your own. So if we go ahead and replace that, we'll get, on the left-hand side, we still have an x, but that y squared dy dx, this piece is 1/3 dv dx. On the right-hand side, we still have x cubed, no problem, but we don't have y cubed anymore. We call that v, and this is exactly what we need to happen. All of our y's are gone. We replace the y function with v, then the dy dx with the derivative of that function should be some manner of dv dx. In this case, we had a 1/3, sure, because we did not have a 3 there. That's exactly what we were looking for. After that, man, this still looks linear. We have a dv dx, we have something that's added to the first power in terms of our dependent variable. Let's make this x over 3 minus v equals x cubed. Hopefully you're seeing the linear a little bit easier at these points. Man, but linear means that we have dv dx by itself, then added or subtracted to a function of x, v to the first. We're pretty close. Let's multiply everything by the reciprocal of x over 3, so 3 over x. So when we do that, we need to write our domain restriction. We know that x can't be 0, but because I'm going to get a linear, and because I'm not going to get an ln over here, notice that I'm going to get x squared. Because of that, I'm going to say that let's just make x greater than 0. That way we don't have to deal with this absolute values, don't run into any other domain issues. So we're going to do this. We're going to get this dv dx minus 3 over x times v, and then we get this 3x squared. That's looking pretty nice so far. Can you do the rest? Can you find our integrating factor? Can you multiply everything by it? Can you do the result of a product rule and take an integral? I bet you can. We should try it. So for us, integrating factor would be this e to the negative 3 integral of 1 over x dx. Well, that's equal to e to the negative 3 ln x is greater than 0. We don't need an absolute value. That's e to the ln x to the negative 3rd power. We're removing that coefficient as an exponent. Inverse functions are composed. We just get 1 over x cubed. Let's multiply everything here in this nice form of a linear by 1 over x cubed. If we do that, well, we still have dv dx, we still have 3 over x times v, we still have 3x squared, but now we're going to multiply by 1 over x cubed. So multiply both sides, every term's going to get it. Oh man, I was wrong. We're going to get absolute value of x. Good thing I had that greater than 0. Now we can start maybe simplifying, probably get ln though. Okay, so on the left-hand side, this is the result of a product rule. We can go straight for that derivative with respect to x of whatever the product of the functions you wouldn't have taken the derivative of. So that's 1 over x cubed times v. On the right-hand side, we get 3 over x. Okay, let's take an integral of both sides with respect to x. So left-hand side, integral of a derivative gives us 1 over x cubed times v. On the right-hand side, we're going to get 3 ln, no absolute value of x, because again, we defined our domain that way. We are going to get a plus c, however. Man, we're almost done. There's only 2 things that we need to do. Let's solve for v as much as possible, and then we'll replace v with the function that we replaced. So we used v to replace a function. We're going to use the function to replace v. Solve for v first, though. Could you take the 3 and make it ln of x cubed? Yeah, you certainly could. Does it matter? It depends. Not really. The only thing that we've got to be concerned about is that what we're going to do here, I think I pointed the wrong thing. What we got to do here is we have to replace the function, the v with the function of y that we used initially. So we replaced y cubed with v. We're going to now replace v with y cubed. And whether you want to write the x cubed first or last, it doesn't really matter. That's the idea. We're looking for a function of y that when you take a derivative of it, you also have the variables and dy dx in there. And that's exactly what we've done. V is y cubed, great. We've got a 3y squared dy dx. No, we just need y squared dy dx. That gives us something a little bit different to substitute, but it's just that constant coefficient. It's not a big deal. So we don't lose it. And it's going to affect this, of course, but it's not going to ruin this sort of technique for us. So nice thing. It comes up with a linear, we make it a domain restriction, and it works out really nicely. So I hope it's making sense to you. I'm going to come back with 2 more examples. Let's try a couple more. So take a look at our differential equation. Homogeneous? Yep, you could write it as homogeneous. Do we have to? No, let's look for an embedded derivative, see that this can be a little bit nicer for us. So instead of dividing by x and y, go ahead and writing, well, probably v to the -1 again, and then v itself, and doing all that stuff, maybe with common denominators. Not super fun. Let's go ahead and find an embedded derivative. What we're looking for is just like a u sub for integration. So we're looking for a function of y like y squared. That the derivative matches up disregarding our constants. So if we take our v equals y squared, and we take a derivative of that with respect to x, since y is a function of x, we have implicit there. We got that chain rule dy dx. And then we say, well, yeah, you know what? Hey, the derivative of y squared is 2y, but it is y dy dx. Let's solve for that substitution. Let's solve for y dy dx. So 1/2 dv dx equals y dy dx. And now we're ready to make this double substitution. One for the function of y, one for the dy dx with a derivative of the function of y attached to it. And that's going to replace every instance of y. That's exactly what we want. So we're going to leave our x, but we're going to get y dy dx is 1/2 dv dx. On the right-hand side, we get x squared plus, we didn't replace the 3, we replaced just the y squared. Now, it's still linear, so we have a dv dx, we have v to the first power, no other cases of v, it's added to that x squared, so let's go ahead, let's write this in linear format. Pretty close, but we know that with linear we want that dv dx by itself. We want the d dependent variable over independent variable without anything connected to it being multiplied. So we're going to have to multiply by 2 over x. Now when we do that, we're going to have a domain restriction because we're multiplying by something where x can't be 0. So I'm not going to show it here, but we're multiplying everything by 2 over x, this whole entire piece. So that gives us dv dx minus 6 over x times v, and then 2x. And we know x can't be 0 in order for us to make this technique work, and that's the domain restrictions. We have to show that, otherwise we get stuck. So how do I do it? I don't know. You got to divide by x, right? Yeah, okay, make sure it's not 0. So let's do that. We multiplied by 2 over x, or multiplied by 2 divided by x. dv dx looks good. We get this minus 6 over xv. Great, that's linear. And then we get this 2x, not a problem. Now, let's find our integrating factor by taking a look at our function of x in front of our v to the first power. If you're wondering why I didn't do x greater than 0, that's in your mind right now, like, wait, it's linear, why don't you do greater than 0? I didn't do it on the first one either, because I saw that that's a power 6. No matter what, that's going to be positive, so it doesn't really matter. Let's see. So this would be x to the negative 6th power. Well, if we think about that, that's going to be 1 over absolute value of x, but then to the 6th power, we would get composition inverse functions, no problem. This is going to be 1 over x to the 6th. That's our integrating factor that we're going to use for this example. Let's multiply everything by that. So we started with a dv dx. We have also this minus 6 over x times v. On the right-hand side, we get 2x. So let's multiply everything by 1 over x to the 6th. And if we simplify just a bit, it's pretty easy to see that we have the result of a product rule. That's kind of nice, because that means that our integrating factor worked for us as far as it's linear. And we can double check it really quickly. See, this is x to the negative 6. We bring down the negative 6, subtract 1 negative 7, put it back. That's the derivative of this piece, which means that this is the result of a product rule. Let's just write the product. On the right-hand side, we get 2 over x to the 5th. And we're ready to take an integral. This looks great. The integral of derivative, gone. We get 1 over x to the 6th times v. On the right-hand side, we'll rewrite that just a little bit, but pretty easy to integrate. So let's take that integral right now with respect to x. So left-hand side, integral, derivative, we get 1 over x to the 6th times v. On the right-hand side, let's make this the integral of 2x to the negative 5th power dx. And that way, when we integrate, it's a little bit nicer to see that. So let's see, we're going to add 1. So adding 1, that's going to be negative 4. Divide by new exponent plus c. Just simplify a bit. It's like negative 1/2, or yeah, that looks about right. So 2, negative 4, negative 1 over 2x to the 4th. We've got a plus c. Let's see, what now? What else has to happen? Well, we still have a v. We're going to have to replace that. But I always like solving for v as much as possible before I do, if I can. So I'm going to multiply everything times x to the 6th power. Let's see if we get that. So multiplying by x to the 6th, that would be negative x squared over 2, or negative 1/2 x squared. Then we have c x to the 6th. That's looking fine too. Let's see, last thing. Hey, we used v to replace a function of y. Let's just replace v with that function of y. It's about as good as we can make it. One thing we could see, you might see a couple different instances here. You could see someone, because we don't really want to solve that explicitly for y, we start dealing with a plus and minus square roots, nasty stuff. So what we could do instead is multiply everything by 2. So if we multiply everything by 2, we could get and if you call this c sub 1, then that 2c sub 1, we can just rewrite that as c. And so 1, if your answers are looking different, they're probably just messing around like this. That looks a little bit nicer. So multiplying by 2, we get the 2y squared. We still have a negative x squared and a 2c sub 1. Call that c sub 1 c, and then we have cx to the 6th minus x squared. And that's how this could look. So just letting you know that's possible. Hope it's making sense. Hopefully you understand that we're looking for embedded derivatives still. I'm just showing you that these can be easier than homogeneous. Let's do 2 more. I'm going to start showing you a slightly different technique. So far, all of our embedded derivatives, they've had to be just v equals a function of y. And that is fine, but it doesn't have to be that way. So I'm going to show you in this one, and man, this is going to make this problem so much easier than we had in homogeneous. So if you think about this as far as homogeneous, if you wanted to write that homogeneous, wow, you'd have to subtract your x. You'd have to divide everything by y. You'd have an x over y. Are you seeing it? You'd have to reciprocate that with a negative exponent, and then you'd have this divided by y. You'd have to put a domain restriction on y so that you'd use a square root of y squared, put that in there, have another v to a negative power and v to the first power, and that gets pretty darn nasty. We spent a lot of time doing that with a homogeneous equation, using that homogeneous substitution. That was nasty. Let's see if this is easier. Now, I want you to notice something. This is, a lot of people would fall into this and go, well, wait. The derivative of this is 2y dy dx. Couldn't I just do that and say, here's y dy dx? I don't know if you could. Is there a better way? Yes. Sometimes what we can do is we can wrap up everything here with a derivative of something involving x's. So I'm going to rewrite this just slightly. I don't look at that and go, wow, you know what? That looks like a derivative of x and y. Wait a minute, I have an x and a y right there. What if we took this whole piece and called that v? Can you use a v with an embedded derivative that includes x's? Yes, it doesn't happen very often. Most times it's just y. But yeah, I can. Let's call this whole thing v and let's just see what happens. Why I think why I'm thinking about that is because even if I call this piece v, it's still going to be nasty because I'm going to have a square root of an x squared plus v. What do I do with that? I don't know. That's really nasty. So what if we can call this whole thing v and then get away with doing a derivative of it and replacing the whole left side? That's going to be sweet. So let's try it. So v is the whole inside piece of this composition idea. Remember that? How we had this obvious substitution? This one's not that obvious, but we're trying to make this embedded derivative work for us in sort of an obvious substitution way. Let's call this whole thing v. Let's take a derivative. Well, now wait a second. A derivative with respect to x. So dv dx, no problem. X squared, the derivative of x squared with respect to x is just 2x. The derivative of y squared with respect to x is 2y, but then we get a dy dx. You go, that doesn't look the same as that side. No, it doesn't. But just like before, we don't care about our constants. Let's solve for the piece that we want to get rid of. Let's solve for the piece that we can substitute. So if we take this and go, let's just divide 2. Wait a minute, so if we factor out a 2, oh, that is sweet. If we factor out a 2, maybe divide by 2. This is awesome. Not only have we replaced the inside with v, that's going to be really nice. Because the square root of v, easy. On the left-hand side, we now took a derivative of v, get dv dx, we got 2x plus 2y dy dx. We said, wait, just divide. Man, if we factor out a 2, then we can replace x plus y dy dx, this entire side, with just 1/2 dv dx. Let's do that double substitution now. So left-hand side, x plus y dy dx, that's equal to 1/2 dv dx. That's great. Every instance of y on the left-hand side is gone. It's wrapped up in a dv dx. On the right-hand side, we'd have square root of v. Wow, wait a minute. That's it? That's it. That's separable right there. We don't have linear, we have nothing as far as being a hard sort of an integral. Let's move our v's dv's, our constants dx. So we have 1 over square root v dv equals 2 dx. Let's integrate both sides with respect to x. Well, that's going to be an integral of v to the negative 1/2 power dv. On the right-hand side, we'd get just 2x plus c. Left-hand side, let's finish that integral off. Let's see, we add 1, that'd be v to the 1/2 divided by a new exponent. Let's see, something divided by 1/2 means multiplied by 2. So this would be 2 square root v equals 2x plus c. You know what I might do? I might just call this c sub 1 and c sub 1 and c sub 1. That way I can divide by 2. I'd still wrap that up as a constant, but I get rid of that too. Let's do that now. So dividing everything by 2. Let's call that c sub 1 over 2 just our arbitrary constant. Are we done? Do we need anything else? Let's see. We have replaced every part, every piece, every term, every factor, everything that involved y's with a v. We used that substitution to create something with a dy dx in it that was a derivative of the piece that we chose for v that was replaced with dv dx. 1/2, yes, because we don't care about constants. That led us to just this really nice separable equation that we do an integral, we've solved it as much as we can for v. I don't want to start squaring things right now. What I want to do instead is, wait, if v is x squared plus y squared, let's just replace that. So the square root of x squared plus y squared equals x plus c. Done. That's as much as I want out of that. If you look back at the same example, when we did it homogeneous, it was at least 3 times the work. So, do embedded derivatives work every time? No, they don't. But when they do work, they typically work really nice. Do you have to only have v equals a function of y? No, that happens most of the time when you get these examples, but it doesn't have to happen all of the time. In fact, if you combine what we think about an obvious substitution with this idea of an embedded derivative, it works really nice. So try that. Try to see if you can wrap up something bigger, and then the derivative is also there. If it is, great. If not, then you have to make something smaller. We're going to try one more example. I'm going to show you something that's slightly different than this. So this was a great example to see. I hope you see it. It's really neat that you can wrap this whole thing up as a v and the derivative is still there. This works occasionally. The next one is a little bit more advanced of an idea. We're going to deal with that one. There's one problem that took a long time. It looked really weird. And I'm going to show you how to deal with it with this embedded derivative. So hang on for that one. All right, let's try one more on this gorgeous little thing. You might remember it because it looks so darn nasty. Really? Yeah, because I need to show you one more thing that we can do. So when we're taking a look at this through the lens of an embedded derivative, and you don't want to do it homogeneous or Bernoulli, and that's what we did the first time. We did this with the Bernoulli equation, so that would be in that video. Back at Bernoulli equation, look at, I think it was like the last one or something. That is just ugly. How in the world is that Bernoulli? Well, If you divide this and you move your y to a -2, you have a y to the -2. That's a Bernoulli equation. And you can solve it that way. Can we make it easier? Yes, but it takes a little looking at, because right now I don't see anything that I can take a derivative of that has a function of y in it that matches up with our dy dx. I don't see anything there. So this is one of the cases where we can kind of outsmart this problem. You go, well, I can't find any v substitution that's obvious. I can't find a v substitution that makes this derivative work for me. So maybe I look at the derivative part. Okay, well, let's think about this. Let's look at x dy dx plus v. You know, that looks like the result of a product rule right there, doesn't it? Yeah. Well, wait a minute. Wait. If this was the result of a product rule, x would be part of the product. Derivative of x is 1. Derivative of y is dy dx. Y would be part of the product. So this comes from the result of a product rule of y times x. Notice that derivative, leave the y alone, dy dx. Derivative of y is 1, and then you'd have a y. Let's call this piece v. And let's just see what happens. So if that piece is v, then obviously the derivative of v with respect to x is going to give us exactly this piece. You know, yeah, absolutely, because we'd say x dy dx plus derivative of x is 1 times y. So that lets us go, okay, I'm going to be able to replace this whole piece with dv dx. Does that make sense to you? Are you getting that? This piece is dv dx. We go, wait, that doesn't help me with my y's. Well, it sure does, because if v involves y's, and here it involves x's also, that's okay. Remember, embedded derivatives can involve x's. They most of the time don't, but they can involve x's. So if this is your function, or sorry, if this is your derivative of dv dx, and it doesn't help you with y's, well, if your v involves y's, can't you just solve for y? As long as x does not equal 0. Should be able to do that. Let's go ahead and make our substitution. So I'm gonna do it 2 different parts. I'm gonna replace this with just dv dx. I'm gonna leave all this alone. X is fine. X is our independent variable. That's okay. So this piece becomes dv dx. We have a 1 plus x to the 4th 1/2 power equals x. And we have a y squared right now. So I want to take a look to make sure this works for you. Was there an obvious sort of a choice for v whose derivative is also up there? No, there wasn't. So we thought backwards. Look at the dy dx. Can you choose a v who, when you take a derivative of it, gives you that piece? Well, yeah. In fact, this is the result of a product rule, x times y. Okay, are those always easy to see? No, they're not. This one was, but they're not always that easy. So if I take a derivative, yeah, dv dx, and then oh my gosh, we get the exact same piece. This whole piece gets replaced with dv dx. I still have a y squared. I'm about to replace it. I still have all this mess of junk. Now, about the y's, I mentioned it, but I want to make sure it sinks in. If you have a v equals some function of x and y, solve for that y and you can replace the y's. It's sort of thinking backwards. Before, in all the other examples, you see the choice of v equals y first, and then you go ahead and find your derivative. Here, we use the derivative to pick our choice for x and y, and then made the y fit it. And that's what we're doing here. So this led to this, leads to solve for y. Oh, now I can replace my y with y over x. Sorry, with v over x. So y squared, no. Let's do v over x squared. And then we have a dv dx. And we still have all this nasty stuff. And you go, well, what's that look like? Does it look linear to you? Does it look like you have a term that's added that has v to the first power? No, it doesn't. In fact, is everything multiplied and divided? Yeah. This needs to be a separable equation for us. So what we're going to look at is that's v squared multiplied by dv dx. That's great. We have an x squared. We've got this can be divided. We have an x over here. Let's write this as a separable equation. So we've already made our domain restriction, no problem. Let's just start simplifying. So v over x squared, we know that exponents distribute across multiplication and division. Let's divide this. Let's move our x's and our dx's on one side. Our v's and dv's are already on the appropriate side. So we're going to get this v squared dv on the right-hand side. Well, if we multiply by x squared, we'll get x cubed over 1 plus x to the 4th to the 1/2 power. And then it's a nice little convention we have that we can separate that that derivative or into that differential sort of form. So let's make sure it works. This led us to the idea of v. Then we use our v to replace our y's, take a derivative to replace this whole mess of crap with dv dx, and man, it works out nicely for separable. So we've separated our variables. We have v's, dv's, we have x's, dx's. We're ready to take an integral on both sides. So left-hand side, let's see, 1/3 v cubed. Right-hand side looks like a basic u sub. How that works is very similar to most of these embedded derivatives where you have to solve for the piece that you're trying to substitute. So du over 4 equals x cubed dx. That's great. So we get this integral. Let me do it here. So we get this integral of x cubed dx. No, we call that du over 4. One plus x to the 4th to the 1/2. No, we're going to do u to the 1/2. Rewriting that just a bit, let's pull the 1/4 out. We'll have integral of u to the negative 1/2 du. That's 1/4. Let's see, we add 1, divide by the new exponent. Plus our constant. 4 times 1/2, that's 2. So 1/2 u to the 1/2? Yeah, but u is 1 plus x to the 4th. And then to the 1/2 plus c. Let's go ahead and write that. What else can we do? What would you do? Well, let's think about replacing v with what v is equal to, but before that, it's often nice to solve for v as much as possible. In this case, we're going to at least want to multiply by 3 everywhere. So I'm going to call this c sub 1, and c sub 1, and c sub 1. So when I multiply by 3, I can wrap that up a little nicer. So v cubed equals 1/2. I'm going to write it this way too, because I'm seeing a fraction here. So I want 1 plus x to the 4th to the 1/2 over 2 plus c sub 1. And now I'm going to multiply everything by 3. So 3 times 1/3 gives us v cubed, okay, times 3 times 3, because I've got to distribute the right-hand side. Now I'm going to wrap this up. I'm going to wrap this up as a c, but I also am seeing this fraction. Maybe I want to write this as one fraction. So here's another thing that we can do. If we put this over 2, well, 3, let's see, common denominator of 2, wouldn't I have to multiply by 2 over 2? Yeah. So I would get this 6. C sub 1 over 2. The point is, I don't care whether it's 3 c sub 1 or 6 c sub 1 or 6 million c sub 1. It's still arbitrary. It does not matter what that is. And so when we write this as one fraction, and we do a plus 6 c sub 1, don't worry about that. Just put a plus c. That arbitrary constant does not matter what that is. You will have this over 2, though. That was the whole nature of getting a common denominator. So rest of this, man, it's just some algebra. Let's go ahead and let's replace our our u with what x is. Let's go ahead and put it over here, solve for v as much as we can. We multiplied everything by 3. We know that arbitrary does mean arbitrary. It doesn't matter what that is. Let's wrap up all of our constants together as a plus c. And now we are ready. Let's replace this v cubed with what v equals. So v is x times y. Don't use this. We already have v's. Use this one. V is x times y. So this would be xy cubed, all this stuff, that means we're going to get x cubed times y cubed, okay? And this is the reason why I chose to write this as one fraction, because now we can divide both sides by x cubed. We already have our domain restriction, we can do that. If we divide by x cubed, we just now have x cubed on the bottom of one fraction instead of splitting this over two fractions. That's the reason why we do it. So instead of rewriting all this, we're going to go, okay, yes, let's just divide everything by x cubed. This is gone, we get x cubed. And that's what we're looking for. We get the same answer done a different way with Bernoulli, but this time we didn't have to deal with a lot of that technique. This was, don't know if it's basic, but it was important for you to see what we actually can do with this embedded derivative technique. Does it always have to be y's? No, it can involve x's, but if it does involve x's, darn well better make sure that it includes the whole entire piece surrounding u by dx, right? Also, and this one's very special, we can go backwards sometimes. So if nothing else is working for you and you see that looks, it's triggering something in your head like, man, that looks an awful like the result of a product rule, do it. Call that v, then solve your v for y, and you can replace all your other y's with v's and x's, and that's exactly what we want. One dependent, one independent variable. Hope it makes sense. I hope that you see the utility in this technique, how it really does make stuff, doesn't look a lot more streamlined, but at least you get another way, and it can be a lot easier than something that's homogeneous or Bernoulli or another technique. So I hope I made this make sense to you. Practice them, start looking for them sometimes. If you look and go, hey, I see that, and the more you do them, the more often you'll start seeing these embedded derivatives and go, I can do it that way. Man, that saved me a headache as far as this technique, because that was really hard. So I would encourage you to go back and look at these examples from the previous videos and see which one you would rather do. Again, people like homogeneous because it's predictable, and same thing with Bernoulli, it's very predictable, but this can save us time. So it's kind of a double-edged sword there. So anyway, we're going to move on, and I'll show you a different substitution technique involving some reducible second-order derivative differential equations next time. Have a great day.